Hi, I'm Rajesh, and I'm at VMware. I'm the memory management tech lead. And Faye, he's the memory management performance expert at VMware. And we will be today talking about understanding virtualized memory management and give you some performance guidelines using Faye will present some of the performance results, and using that, he will present some guidelines. This is a disclaimer, standard disclaimer. I will leave it for a few seconds so that you can read through this. Okay, I will briefly motivate the talk. Like a lot of you guys are here, so there is clearly you are motivated. But I'll give you very brief questions that often that's asked in memory management, and using that, we will guide our talk also to using those motivations. And then before we jump in the performance implications and the guidelines, I would introduce some of the memory management concepts so that it is clear when we actually talk about the guidelines and the performance results and etc. And then Faye will present a lot of performance results, and using the results, he will provide you some guidelines on how you want to set up your system and provision VMs, etc., to get a good performance when you overcommit memory. And finally, we will summarize, and hopefully we'll have some time for question and answer. Regarding the question and answer, there are 2 mics over there. So if you have some questions, you should come to the mic and ask so that everybody can listen to you. Motivations. So when you deploy, when you buy a ESX machine, and then the first few questions that come in is, how am I going to set up my VMs? Like, how big this, so I have to set up this 100 VMs. These VMs has to be 4 GB VMs or 8 GB VMs, or what is the right sizing of these VMs? How am I going to right size the VM's memory size so that I get optimal performance? That's often that comes up in mind. If you set that VM to be too large, yeah, it is very conservative. It'll accommodate all sorts of workload then. But the disadvantage is now you will spend too much of overhead, and unnecessarily you have allocated the VMs to be too big than necessary. So you are clearly underutilizing the hardware. So you don't want to over-provision the VM too much. And then, so once you decide on some VM's memory size, then the next question comes is like, how many such VMs I can place on this host? And I really don't want my customers or my users to feel any performance loss or pretty poor performance, and thereby they will keep complaining. So the next question is like, how many VMs I can place on this ESX host? Now you can decide using these 2 parameters. You can decide you are likely making decisions about, okay, am I going to overcommit or not? It may be that in some setups, like particularly like a desktop environment, and other cases, you might want to overcommit memory. In that case, how should I overcommit? Should I overcommit with 100 more VMs, or how should I overcommit? Or how much I can overcommit without affecting the performance too much? That's another question often comes up, right? So we will try to answer these questions, and then we will give you some guidelines on how you may want to do these things while you are setting up deploying ESX. So as I said before we jump into the performance things, I would like to introduce some memory management concepts so that it's clear when we talk about the guidelines and the performance and etc. So when you talk about memory management, you have to take a holistic angle, right? Because underneath, if you see we are running ESX, and the ESX machine probably has 2 terabytes of memory or something like that. And ESX is taking that memory and then giving it to a bunch of VMs that is running on top of ESX. Now, those VMs in turn, the guest OS running inside those VMs, are taking that memory that is provisioned for them and then giving it to a bunch of applications. In this example, I'm pointing out the Java application. You may configure the Java VM And then you may say that, oh, the heap size for this Java application is like I'm allocating some 5 GB of heap for that Java application or something like that. And then each layer, it's almost like a wedding cake, right? Each layer has different flavors and different flavor of memory management. ESX does one flavor of memory management, the guest OS does another way, and Java uses some garbage collection for its own memory management, right? So each layer uses a different kind of memory management. So that is why it is kind of pretty difficult when in a virtualized environment. You have to understand all these layers to an extent to get a good feel for how I should provision my VMs, how I should deploy my applications to get a reasonable, good performance, even when I overcommit. The another main thing that happens in this is every layer in this assumes that it owns memory that it is configured with. What I mean by that is, if you have a VM and you configure with, say, 20 GB of memory, that VM assumes that it owns the 20 GB. It does not know, it does not care that there is underlying ESX running. Maybe in the ESX side it is over-provisioned. Maybe so it don't have to. It is better to give up whatever memory it is not using. It is better to give up to the ESX. Normally, VMs do the VMs in this case don't do that because it's layering. That's how we build software, right? Like each layer is independently works and it thinks that everything, all the resources it owns, and does optimizations based on that. For example, when a layer like a guest OS, when it has a lot of free memory, oftentimes what it does is it goes and caches some of the disk data because the Windows OS assumes that, oh, you may run the Word application. So let me bring the Word application data or Word application pages into the memory before you access it, so that whenever you start the Word application, it can be super fast. So that is what we call file cache or super fetching or something like that. So there is what I want to nail in this slide is the cross-layer knowledge is pretty limited, and because of that, we have to build sophisticated techniques to make the reclamation work. And we will talk about some of the techniques that we built and how it works. And so before I jump into further details, I will broadly classify the memory into these categories. Like there is a total configured memory for each layer, like guest OS or ESX or for everyone. There is a configured amount of memory is there, and some of this memory is allocated to either VM or the VMs are allocating to the applications. So there is an allocated memory, and then there is a free memory, right? So that's all. Like if you see it from the ESX only knows what is allocated and what is free. But it allocated, say, a 10 GB to a VM, it does not know what the 10 GB is used for, how the VM is using the 10 GB, whether it is using it to run a Chrome application or whether it is running using it for Word application. It does not have an idea of that. So at level, all it knows is allocated. That's not very nice, because then ESX cannot differentiate between, oh, this is the VM is more important because it is whatever memory I allocated to it, it is utilizing it properly. Whereas the other VM, I allocated 10 GB of memory, it is just sitting idle with that memory. At least the ESX should be able to differentiate between these two active and idle VMs. So hardware has given some techniques to figure out whether allocated page is used or not. So we have similar those hardware techniques, and then ESX and all this layer, even guest OSs, normally at least can broadly classify the memory into active and idle. So that is very important while we talk about memory overcommit and how we allocate memory. So I'll just want to introduce that allocated memory can be broadly classified into active and idle, and then there are ways to figure out how much is active and idle. Now, before I jump in, let me say what I mean by memory undercommit. Like oftentimes you may decide that, okay, these are very super important applications. I don't want to do any memory overcommit. I am ready to provision as much memory as you want. In that case, the total size, what I mean by memory overcommit is the total size, configured size of the VMs is less than the actual host memory size. In that case, for ESX, there is no reason to reclaim memory from any of these VMs because there is no need. It has a bunch of free memory. Even after allocating the memory to the VMs, the ESX is left out with more free memory. So there is no need for it to allocate. And then when reclaim from the VMs, and in this case, ESX just allocates whatever the memory the VMs wanted. In this case, there are 2 VMs with the 10 GB each, allocated 10 GB to these VMs and happy with it. That's a easier case. But when overcommit hits, what I mean by overcommit here is when the sum of the guess configured size of the VMs is bigger than the host memory. In that case, ESX cannot fit all the VMs in memory, so it has to do something. It has to reclaim some memory from some of these VMs so that it can accommodate all these VMs on this host. Now, while doing that, ESX would like to give more memory to the active VMs than VMs that are just sitting idle. You may have a bunch of users, and all of them are desktop users. Some other users have gone for lunch or whatever it is. It is better to take away memory from those VMs and then give it to VMs that are being actively used right now, right? And then once ESX decides that, okay, I'm going to give X amount of memory to VM1, Y amount of memory to VM2, now it is possible that the amount of memory allocated to a VM is smaller than its configured size. In this case, the VM2, ESX allocated some memory to it, but as I shown in the figure, if you see the active VM, the VM1 has more active memory, so it will get most of the memory it likes. And then the VM2 will get a little bit lower than what it wants. So we have to reclaim the memory from the VM. So we have various techniques that we will talk about it later in the slides, but we have designed various innovative techniques like ballooning, page sharing, etc., to reclaim the memory from the VM. Particularly in the VM2, I'm showing there are some amount of memory is ballooned, some amount of memory is swapped out, and etc. Now, as I said, ESX determines how much memory it allocates. So there are 2 steps in the process of allocating and then reclaiming memory. One is, compute an entitlement. We call it as entitlement. How much memory a VM gets. That's what we call it as entitlement for the VM. The entitlement of a VM, ESX computes entitlement for each VM that is running on the host. And once it computes entitlement, then it sees that, okay, whether the VMs, whatever the current consumption is within the entitlement. If it is within the entitlement, then you don't have to do anything. But if the VM's current consumption is more than the entitlement, then ESX has to reclaim some memory from that VM. And then as administrator, ESX administrator, you can control this. You can give some parameters to this entitlement algorithm. So say that, oh, this is my important VM, and I want it to get all whatever it wants. So in that case, you can go and set a reservation for that VM. Otherwise, we have other parameters like limit and shares. We'll talk about it in the next slide. So that you can influence the entitlement algorithm and help ESX in allocating memory to the VM. And then in addition to the user-specified parameters, as I pointed out previously, ESX classifies the VM's memory into active and idle. And then using that, it allocates memory to the VM. We detect actually how much is active and how much is idle. It is very kind of simple technique. Like what we do is we take some 100 pages from the VM, randomly choose 100 pages from the VM, and wait for a minute, and then see how many of these 100 pages were actually used in this minute. And then we will use an average over time to compute, okay, this VM seems to be using 50% of its memory. Or a very rough estimate, right? That's a good enough rough estimate for us to allocate memory well. So we use that simple sampling technique for getting the estimate. This is the same way of sampling is done in the election time. People say how many seats Democrats will win. All that is similar sampling-based method is used. We use similar sampling-based method here. So I was talking about various entitlement parameters that administrators can provide to guide ESX. One of them is clearly the configured memory size. Every VM has some memory size. In addition, on the right-hand side, I'm showing a VM with some active memory and idle memory. If you really want to ensure that this VM always gets its active memory, maybe you may want to put the reservation above the active. Like you follow some of the parameters and then see that, okay, this VM needs this much memory. I have a 20 GB VM. and I'm always running a 10 GB Java workload inside, and I better want all the Java heap to be allocated. So in that case, you may want to set the reservation above that, like something like a 12 GB or something like that. In some odd cases, the user really wants, one of the cases is, example is, the user really says, no, I want to get the 16 GB of VM. You know that he does not need a 16 GB of VM, but he says, no, I want a 16 GB of VM. In that case, as an administrator, you can provision a 16 GB of VM, but from the physical resources, you want to allocate only, say, 12 GB to that VM. In that case, you can set the limit, and then go and say limit is only 12 GB, which then ESX will ensure that the amount of physical memory allocated to the VM is only 12 GB, never more than that. And there are other cases where you don't want to set this strict reservation and limit things. Rather, you want to say, oh, I have this bunch of VMs, and out of this VM is twice more important than the other VM. So it's like some priority. In that case, you can set up shares. Shares is like some priority. So you can go and set shares values. And then ESX, proportional to shares, ESX allocates memory. So these are the user, the first 4 parameters are the user configured parameters. And then the final one is the active estimation that I was talking about. ESX uses the active estimation to figure out how much memory the VM is utilizing, and it uses that also into the entitlement computation. So ESX uses all those 4 parameters to compute some entitlement for a VM. Now, it is possible that the entitlement is smaller than the current consumption of the VM. Like currently, like you configure a 20 GB VM, and the entitlement turned out to be 12 GB or something like that. In that case, ESX has to reclaim the 8 GB of memory from the VM. We use 4 different techniques to reclaim memory from the VM. Transparent page sharing, which is a background thread that runs and figures out duplicate pages and collapses them. And then there is a beautiful technique called ballooning, which initially I was talking about layering, and each layer is very independent. This ballooning is a method to introduce the ESX level memory pressure into the VM. And then we have compression, which basically compresses some other pages and keeps it in memory. And then we have swapping. I'll talk about each technique in the next slides. So transparent page sharing is like we have, say that in this case we have 2 VMs and then they are running Windows 8.1 or something like that, identical OSs, and then it has identical application, same version of Chrome is running inside. Now initially if you see, the ESX has 2 copies of this, like the OS and the Chrome, there are 2 copies of the image, and normally a lot of guest OSs zeros its free pages. So there are a lot of zero content that is on the physical memory. Now ESX has a background thread. It is which goes and scans all these pages and computes a signature for each content of this page. What I mean by page is like the VM's memory is divided into 4 kilobyte chunks, and for each chunk of this 4 kilobyte we compute a signature, and using the signature we can find out immediately that these 2 pages are duplicate, and we collapse them into 1 page. And when we do that, then if you see, like we can collapse both the OSs to 1 set of OS pages and both the Chrome to 1 set of Chrome pages, and similarly all the 0 pages can be collapsed to 1 single 0 page. Because of that, we save a lot of physical memory, and that saved physical memory now can be used for placing more VMs on this host. And transparent page sharing is a very low-cost technique. The scanning is done at a very low rate, and so you won't see much CPU loss because of that. We keep it very minimal. So it is one of the most low-cost technique to get memory reclamation. The next technique is ballooning. In this technique, what we do is we want to introduce the host-level memory pressure into the VM. So what we do is we put a balloon driver inside the VM, and whenever ESX wants to reclaim some memory, say that in this case you have a VM running, VM1 running, and as I said, inside the VM you can say that some memory is actively used, some memory is idle, and I talked about superfetch, like sometimes like guest OSs, whenever it is a lot of free memory is there, guest OSs cache some of the disk data, so there's cache memory and the free memory. Now, ESX initially it was all fine because there is no overcommit. Then you say that there is a VM2 comes in, powers on. And in that case, VM2 comes and allocates some memory, touches some memory. So ESX allocates the memory. Now ESX is running out of memory. So what it does is, okay, it goes and then assume that the VM2 is a super important VM. You have full reservation for that VM. In that case, now it has to reclaim some memory from this VM1. So then at this situation, ESX calls a balloon driver and then says, oh, can you reclaim some 2 GB for me? Then what balloon driver does is it goes and allocates memory from within the guest. And then it pins the memory. It pins the memory. What I mean by pinned is whatever memory it allocates, it makes sure that the guest OS does not swap out that memory or do something like that funny things with that memory. It just allocates pinned memory from the guest OS, so it is always there. Once it is balloon driver is allocates, we wrote the balloon driver. We know that this memory, the balloon driver is not going to use this memory at all. So since it is our balloon driver and we know what it is doing, what we can do is whatever balloon driver memory it wants, we can go and free the memory from the ESX side. So that's what happens here. So you get now ESX has some more free memory. Now the VM2 goes and allocates that also. And now again, like ESX determines, oh, okay, I have to balloon more. So it goes and balloons more further from the VM. At some point, like there is enough ESX free memory, so VM2 allocation is satisfied. Now, if you see the balloon driver, is another very cheap technique to reclaim memory from the VM. But one thing is it has some side effects because we are allocating memory from within the VM. So it is possible that sometime it might lead to swap. We will talk about it in the next slide. And I was telling that balloon driver, we just free the memory underneath. Sometimes what we do is we free the memory and then back it with a single 0 page. So what I was saying is balloon driver may allocate memory within the guest. This is another view of the guest. Above I showed the last slide view where active, idle, cache, and free. And below I'm showing a little bit different view, where I'm saying what is the purpose of the memory. OS allocates some application pages. These are ESX does not know actually what the pages are being used for, but I'm just showing a different view of this one. So there is some memory is allocated for the apps, some memory is cache, and some memory is free. Now, if you see our balloon driver, we started initially ballooning. Normally, when we balloon, guest OS initially allocates the free pages. And that time, there is no side effect because of that. And then, even if you further balloon, normally guest OS goes and takes out the cache pages. Again, cached pages are just for performance optimization, and it is not actively used at this point. So it is okay to take that memory, and it won't have any performance impact. Now, if you further balloon, that's when it is possible that you go and hit the actual application pages. And when guest OS have to reclaim some application pages, that's when it has to store and restore the contents of the application pages before it frees that memory. So that is when it will hit some guest level swapping. And normally this situation is rare, but you can hit this situation when you force a guest level paging. And then there are some other side effects we have to wonder about, because since we are allocating memory from the VM, you have to be careful about what memory is pinned and what memory is allocated as large pages inside the guest, because sometimes once it is allocated as large pages, you cannot reclaim via ballooning. So we take care of those are the corner cases here. And then swapping and compression. Like if page sharing and ballooning is not able to reclaim all the memory we would like to reclaim, then we use swapping and compression to reclaim the memory from the VM. So in this example, I have just one VM, but it's a big VM, 20 GB VM, and the ESX host has only 8 GB of memory. So initially, what happens is regularly VM touches the memory, ESX allocates that memory. At some point, ESX says that, oh, I'm running out of memory. So as we talked about before, initially we will balloon. That is our preferred approach when we have to reclaim some memory from the VM. So we balloon some memory. Still, that is not enough because ESX, the VM further allocated the memory, whatever we could balloon out. So ESX now has to reclaim more memory from the VM. So in that case, what ESX will do is, okay, now balloon driver for some reason cannot take out more memory from the VM. So in that case, ESX has to use some hypervisor level swapping to free the memory from the VM. It stores and restores the contents via the swap file. Clearly, reclaiming memory via swapping is a little bit costly because you are now writing the content to the disk, and then whenever it touches, you have to read it back, and etc. Right? So that's a little bit costly. So we thought about, okay, how to improve all this. So then two releases before, we implemented another technique where instead of actually swapping, before swapping, what we try to do is we actually compress the pages. So we know that these pages we have to reclaim, and we go and compress the contents of the pages. Sometimes a 4K page can be compressed into less than 1 kilobytes or something like that. So you can really, sometimes even few bytes actually. So you can really compress this page, and then we can only store the compressed content in the memory, and that thereby saving a lot of physical memory. So that we introduced in 2 releases before, and so we can just compress the memory and avoid any disk writes and disk reads. And then once you have compressed memory, like the VM now can allocate all the memory it wants. Now, so these, like this, like in addition to compression, we introduced another swapping to SSD, because SSDs are clearly faster. So I released 2 releases before. We introduced like swapping to SSD, which also helps to reduce the cost of swapping. So we have these 4 techniques, like transparent page sharing is, as I said, is very low cost, so it is always running. Whereas ballooning, compression, swapping is a little bit costly. But the question is, when do we use one of these techniques, balloon, compress, or swap? So this is one which shows that high-level algorithm. It depends upon what is the memory state of the ESX. If ESX is critically low in memory, that is, if it is 4%, that is our threshold is 4%. If the host has more than 4% of free memory, then normally we use ballooning to reclaim the memory. But it is possible that sometime like the ESX is critically low, that is, it's below the 4% mark. In that case, we will have to reclaim the memory from the VM forcefully. In those cases, we'll use compression first. If the compression is not successful in compressing the page below 50%, then we go and swap out that page. Similarly, on the opposite side, if suddenly, like, initially the ESX was overcommitted, so we reclaimed the memory, and then you powered off 10 VMs. So the ESX now is no more overcommitted. In that case, what we do is we go and release out all the ballooned pages back. For the swapped out memory, the VM, whenever it touches, it can read in these pages. So that concludes my portion of the talk, concepts, and Faye will talk about, show some performance results, and give you some guidelines on this.
Hi. So in the rest of the talk, I'm going to show some performance data to help you understand the performance implication of all the ESS memory reclamation techniques, and come along with some best practices. Before showing the data, I'd like to emphasize one thing. So all the ESS memory reclamation techniques are designed to handle burst memory pressure well. So if your server is experiencing, let's say, constant memory pressure, then this situation should be handled by higher level memory management like DLS or vMotion. So the key point here is, so don't expect ESS runs well if you give him, let's say, 10x memory overcommitment. It won't happen. So in this talk, I'm going to cover the following aspect. First, I'm going to talk about how to properly size a VM, and some interactions between page sharing and the large pages. Some performance implication about the ballooning, memory compression, and swap to SSD. So here, the term we use is swap to host cache. Host cache is essentially just an SSD. In the last, I'm going to talk about how to safely memory overcommit a host. The tools that we used in all the experiments includes some very commonly used tools like vCenter performance chart, ESStop, and memstats. So all these tools are available with the standard vSphere product. When you know your host has a performance issue, these tools will be very helpful for performance troubleshooting. Another tool is vCenter operation, which is also well known as VCOps. You can use it to monitor the performance from a higher level in the cluster and the data center level. It can not only tell if you have a server has a problem or not, but also tell you what the root cause of the problem. One recommendation that I want to give is please consider use the custom UI of the VCOps instead of a standard UI if you don't know about that, because it provides much more useful counters and useful information. If you have not tried that, please give it a try. So you will be surprised. Next, I'm going to show how to use VCOps to help us to determine proper size, memory size for a particular VM. Basically, the VM should be sized to guard against the active memory reclamation. From the guest perspective, to avoid active reclamation, which means to avoid guest level swapping, the VM memory size should be set to be larger than its highest demand during the peak load. Another benefit of lowering the memory demand is that, if necessary, we can set the reservation above the memory demand so that the active memory will not be reclaimed from the host perspective. Next, I'm going to show you them how to find the guest demand by using the VCOps. In this particular example, I showed the guest memory demand of my workstation VM in the past 24 hours. Here you can choose a history of past 24 hours, or even a history of past a few days, a few weeks, or even a few months. From the figure, you can find what is the highest guest memory demand and what is the lowest memory demand. In this particular example, because my workstation is almost idle, so if you see the highest memory demand is only about 250 MB, which is pretty small. But the key takeaway here is that the VM's memory size, the VM should be sized based on its memory demand. Next, I'm going to talk about the performance implication of each memory reclamation technique. As Rajesh already mentioned, page sharing is a very low-cost technique to reclaim memory, but many of you may already know that when host large page is used, page sharing is not working anymore. So I'd like to take this opportunity to clarify some interactions between page sharing and the large page. So the first thing I want to emphasize is actually the memory saving from the page sharing can be quite significant for homogeneous VMs. So in this example, I run 2 experiments with multiple swing bench VMs and the VDI. VDI is a stand for the virtual desktop infrastructure, so runs a bunch of desktop VMs. If you look at these 2 setups, for swing bench VM, there are actually 43% of guest memory are shared, while for VDI VMs, there are 75% of guest memory are actually shared. In terms of saving, about 34% of memory from swing bench can be saved from the page sharing, while 73% of VM from VDI workload can be saved from page sharing. By looking at the shared memory, they can actually be classified into 2 categories. One is the intro-VM sharing, which is a self-sharing within a VM. Another type of sharing is the inter-VM sharing. It is sharing across the VM. So the percentage of each type is actually quite workload dependent. For example, for swing bench VM, there are actually 55% of shared memory are inter-VM sharing. Well, this value is very small for VDI workload. Only 70% of memory are inter-VM sharing. This is mainly because VDI workloads typically run the Windows guest operating system. A lot of the sharing comes from the 0 pages, which is counted as an intro-VM sharing. The workload homogeneity actually mostly affects the inter-VM sharing. So if you run heterogeneous workloads in the host, you will expect to see less inter-VM sharing. Page sharing is a very powerful technique to saving memory, but there are some guest and host features can prevent it from happening. For example, many guest OS actually have this feature called address space layout randomization for security purpose. Academic studies has shown that with ASLR feature, you will expect to see less than 50 MB sharing reduction. So this reduction is kind of very small if compared to the VMs with big size. So don't worry about it too much. Well, another feature is called super fetching. So it essentially just proactively caching the files from disk to memory. This feature indeed largely reduces the amount of sharing. So it is a problem. Well, well, the superfetch actually hurts performance when a lot of VMs run together because it significantly increases the number of IOs if you run a lot of such VMs in the host. That's the reason in our VDI environment, we actually suggest customers to turn this feature off. But from a host perspective, if your host uses large page, the ESS will not share the large pages. However, one thing that the pages are not shared, but the page sharing scanning thread still works, which means it still generates hashes. The hashes is a hash of orders. It still scans all the 4 KB small chunks within a large page and compute the hashes and save those hashes in the VM kernel. This hash will be very useful because later, for whatever reason, the large page is broken for whatever reason. Now all the small pages within the large page can be shared very quickly with those hashes available. So that's why the page sharing scanning thread still works. At this point, you may be disappointed about large pages because it completely eliminated the page sharing. Then why do we use large pages in the first place? This is mainly because using large pages can improve performance for a lot of workloads due to the fewer TLB misses and a faster page lookup time. For example, comparing to the baseline case where both the guest and host using small pages, when both guest and host use large pages, the performance for SpecDB workload can be improved by 30%. Then that's the reason why ESS enable host large pages by default. Then how does large pages impact the memory overcommitment? Clearly, with large pages, it brings a higher memory pressure because there is no sharing. Then it is easier for ESS to trigger memory reclamation using ballooning or swapping. However, a large page may be broken when any of the small pages within the large page is ballooned or swapped. Then page sharing can happen thereafter. Here I show an example of swing bench VMs when memory is overcommitted. So this figure looks a little bit complicated, but the point here is when ballooning or swapping happens, the total amount of the large pages within the host showing in the yellow line reduces. And as a result, the amount of the page sharing starts to happen, showing in the green line. So effectively, large pages delays page sharing until memory is overcommitted. In summary, so please don't, always enable page sharing, even if the host large pages are used, because otherwise, the page sharing scanning threads won't generate the hints for the small pages, and this situation is pretty bad when memory is overcommitted later. In terms of large page, so you can consider disable it only when high consolidation is desired. For example, in VDI environment, and applications are well understood, such that they are not benefited from large pages. There are indeed some applications that don't benefit from large pages. As I said before, when you use large pages, it is easier to trigger memory reclamation, such as ballooning or swapping. Then how can we use them efficiently? For ballooning, it is clear that we should always install VMware tools and enable ballooning for all the VMs because ballooning is usually much better for performance compared with host swapping. By the meantime, as Rajesh mentioned, the ballooning may cause guest swapping. So we should provide sufficient swap space inside the guest, because otherwise the application may be killed by the guest operating system out of memory killers when balloon inflates. If possible, please consider put the guest swap partition on a separate virtual disk. Then this allows us to monitor swapping activities from the host by just looking at the stats of this virtual disk. Note that using ballooning to reclaim memory taking some time because guest memory allocation cannot be done immediately. Well, in the case where the host free memory drops too quickly, we have to use host swapping to reclaim memory. We have some performance optimizations to help improve the host swapping performance, which is memory compression and swap to SSD. Basically, in SS, before we actually swap out a page, we were trying to first, indeed, we try to share this page. if the page has not been picked up by the page sharing scanning thread. If the page is not shareable, then we try to compress this page. So that ESS only compresses the swap candidate page, which means we will not proactively compress the regular VM memory. If the page is not compressible, lastly, we can try to swap it to a host cache, which essentially is a SSD. Now let's see how much performance improvement we can get from the memory compression and the swap to SSD. This figure shows the memory compression results. In the experiments, I run 16 swim-bench VMs with a total 80 gigabyte config memory. This figure shows the normalized throughput of all the swim-bench VMs while I change the host memory size from 96 gigabyte to 50 gigabyte. As you can see, when memory compression is used, the performance can be improved by more than 50% in the highest memory with the highest memory overcommitment ratio. This is mainly because by compressing more pages, and these pages we are not going to disk anymore. So therefore, by looking at the swapping rate with memory compression, the swapping in the memory is reduced by 80% in the highest memory commitment case. This significantly improved the performance. This figure shows the results from the swap to SSD. Again, I run 12 swim-bench VMs with total 60 gigabyte configured VM memory, and the SSD size is about 40 gigabyte. Again, the figure shows the normalized throughput of all the swim-bench VMs while I change the host memory size from 72 gigabyte to 20 gigabyte. The results are normalized to the case where the memory is end-committed. So as we can see, with SSD, when SSD is used, the performance can again improve by more than 50% in the highest memory overcommitment ratio. This is mainly because the SSD reading latency is much smaller compared to the disk reading latency. Therefore, by looking at the page 14 latency, when using SSD, the latency can be reduced from like 3 milliseconds to a few hundred microseconds. So it's a very big reduction. This significantly improved the performance. Given the obvious benefit from memory compression, so we enabled it by default, so please don't disable it. Well, host cache is a nice to have feature because nowadays SSD is getting bigger and bigger. One can easily get hundreds of gigabyte SSD with a reasonable price. So host cache can be just a small portion of the SSD, let's say 20%. This is because we assume that host swapping should be a rare event. So if you configure too big SSD just for host cache, it's potentially a waste. So far, we have talked about the performance implication of each memory reclamation techniques. But I guess a more interesting question to you guys is, how can I safely memory overcommit a host? Next, I'm going to talk about some memory overcommitment guidance about how to safely memory overcommit a host. Before answering the question how to overcommit a host, I'd like to refine the concept of memory overcommitment. There are actually two types of memory overcommitment. The first one is a configured memory overcommitment, which is sum of all the configured memory size of all VMs divided by host memory size, which is also the concept described by Rajesh. I'm going to introduce a new types of memory overcommitment, which is called active memory overcommitment. It is the sum of the active memory of all VMs divided by the host memory size. In terms of performance impact, when active memory overcommitment is close to 1, it is very likely that your server will have a performance degradation, because some active memory will be reclaimed. They are not in physical RAMs anymore. But for one configured memory overcommitment is larger than 1, as long as your active memory overcommitment is smaller than 1, you should expect to see very small performance impact, because most reclaimed memory come from the free or idle guest memory. That being said, we should always target for high consolidation ratio by keeping the configured memory overcommitment larger than 1, while keep the active memory overcommitment smaller than 1. Then the question is, how do we know the active memory of the VM? We can use a VCOps to track VM's average and maximum memory demand over time in the history, and this is pretty good proxy for the active memory. But what if I don't have VCOps installed and somehow I don't have any idea what is active memory? Then we can just simply monitor some performance counters when you keep adding VMs to see if we have a performance problem or not. Now you may be curious what these counters are, but before I talk about the counters, I'd like to first talk about some counters that we should not look at, because sometimes looking at the wrong counters is worse than not looking at any counters at all. So the first counter is consumed. The consumed memory is because for consumed memory, the memory allocation varies dynamically based on its entitlement. So if you see a VM with very, very small consumed memory, it may be simply because this VM is just idle. So this consumed memory doesn't imply any performance problem. Another set of counters that is sometimes very, very confusing is the memory reclamation related counters, such as we have in our VC performance chart, we have counters show the ballooned memory, the swap use memory, the compressed memory, and the shared memory. We have all these counters exposed to you. Well, these counters sometimes misleading because the non-zero values for these counters just mean that the memory reclamation has happened before. It doesn't necessarily mean that you have a performance problem now. Now, I show you an example. So in this particular example, I run 6 4 GB swing bench VMs in a 16 GB host. And the VM 4, 5, 6 are idle, so I'm not going to show these VMs in the figure. In the top figure, I show the operation permitted of each individual VM, and at the bottom figure, I show the counter values for all these 4 reclamation-related counters. VM1 runs the workload from the beginning. After 10 minutes, VM2 runs the workload. And up to this point, the host memory is not overcommitted. So if you look at those counters, they show almost close to 0 values. After 20 minutes, I let VM3 run the workload. Then at this point, the host memory is overcommitted. As you can see from the bottom figure, all the counters values start to show up. You see high balloon memory, and you see some shared memory, some swapped memory, etc. Well, know that VM3, I just let it run 10 minutes. After 10 minutes, VM3 stops the workload. Then from this point of view, the memory is not overcommitted anymore because the VM3 goes to idle. Well, if you look at those counters, you see we still show very high balloon memory in the system. Well, when you look at the performance of VM1 and VM2, they are not impacted at all. This is mainly because that the high balloon memories mainly come from those VM4, VM5, VM6 come from the idle VMs. So that's the reason those counters cannot be used to identify performance problem. Now, what should be the counter that we should watch for? The first counter is swapping rate. If a VM has a constant non-zero swapping rate, then which indeed your VM is experiencing performance problem. The next counter is called latency, which shows the percentage of time the VM is waiting for decompression and swapping. So this counter provides a good estimation about the performance impact due to memory compression and swapping, because if a VM spends, let's say, 10% of time on waiting for decompression and swapping, it is very likely that you will see more than 10% performance slowdown. The next counter is active. So if your VM's active memory is really small, the reclaimed memory from this VM is less likely to be a problem. The last set of counters are virtual disk read and write rate. So these 2 counters are very specific to the virtual disk that has a VM swap partition if you configure your VM in this way. Because then if you see constant non-zero read-write in this particular virtual disk, which means your VM is doing get swapping, it is possible that the balloon driver is causing the problem. Again, I'm going to show you an example to see how to use one of the counters. Same experiments. Instead of making 3 VMs idle, or during the all time, I make all these 3 VMs run the workloads. The top figure shows the operation per minute for each individual VM, and the bottom figure shows the counter value. Here I choose counter swapping rate. Again, VM1, VM2 runs in the first 20 minutes. At this point, there is no memory overcommitment. The counter always gives you 0. There's no swapping. Well, after 20 minutes, I let all other 4 VMs start to run workloads. Then the host is severe memory overcommitted. As you can see, we see a constant non-zero swapping rate in the host. By looking at the performance of VM1 and VM2, they are significantly degraded. Therefore, we can use the swapping rate counter to identify the performance problem. So in summary, in today's talk, Rajesh has briefly described some concepts about the memory, ESS memory management. Some key takeaways are VMs achieve best performance when its entitlement is greater than its demand. And assuming there is no limited set, the VM memory is reclaimed only when host memory is overcommitted. And ESS always choose the lowest cost reclamation technique based on the free memory stays in the host. In terms of performance, I have introduced some counters to watch for performance issue. And I recommend you use VCOps to kind of track performance and finding the guest memory demand. VM memory should be sized based on its memory demand. And we should always enable ballooning, page sharing, and memory compression, and use SSD as host cache if possible. The one last thing that I want to emphasize is that the transient memory pressure is not a problem. The ESS memory reclamation techniques should handle it very well. So the last slide shows a bunch of other performance-related sessions that you may be interested in, and we are happy to take any questions. Thank you.
Thank you. We have a few minutes. Yeah, go ahead.
So you mentioned that pages that are swap candidates are also checked for compression first. Does that mean that pages that are swapped have been evaluated for compression and it's been determined that that's not a good technique for them, or are they swapped in a compressed state?
Yeah, the question is like whether the pages are compressed and then swapped out. Otherwise, we just try to compress. If not possible, then we swap out the uncompressed page. The answer is the second, where what we do is we initially try to compress it. If it can be compressed within 2 kilobytes, then we store the compressed image. But if it cannot be, then we just swap out that 4 kilobyte page onto the disk, and we read the 4 kilobyte page back.
So just to clarify, if it can't be compressed more than 50%, then
Yeah.
it's swapped in its uncompressed state.
It is swapped out in an uncompressed state.
Thank you.
Yeah. Go ahead.
This one?
Hello?
Yeah.
Can you please provide a little bit detail about how does the VMware tools help on memory reclamation and memory optimization?
So the VMware tools inside the guest you are asking, right? Mm-hmm. So the VMware tools is the one which has the balloon driver. So VMware tools is the one which installs the balloon driver. So when you install the VMware tools, that's when we are installing the balloon driver inside the VM. So without the balloon driver, we couldn't do the ballooning technique to reclaim memory from the VM. So we encourage you to install the VMware tools so that the balloon driver gets installed inside the VM.
Okay. So are there any ESX operations that can track the memory performance on the virtual machine?
Normally we cannot, because it's all different guest OSs, different things, right? Like each version will have different types of counters inside the guest OS. So it is hard for us to track all the performance metrics inside the VM. But we have tools like Hyperic and other things which help you to collect some of the data from within the guest OS and provide it outside. So, but this is out of topic for this.
Yeah, I'm asking, is there any host ESSI operations that can monitor?
Right. So the only operation, as I said, is you can we broadly classify the memory into active and idle. You can see the active, how much is the active memory. Other than that, we don't provide too much clarity into how much guest memory is, how it is used, and what is its performance, and etc. Go ahead.
It didn't come clear to me about the large page guest large page problem. I don't know if I understand correctly, but in Linux it's not that a big issue because the balloon driver is aware of that, and in Windows is not. What is the difference? It hurts more in Windows or Linux?
Yeah, it's right. I think when the Linux guys implemented large pages for the first time, they implemented like even the large pages cannot be ever reclaimed by anyone. So that is why we had to do that. We had to make sure that whatever number of large pages is allocated inside the Linux, we won't balloon. Whereas the Windows didn't have that problem, does not have that problem. But now Linux implementation of large pages is also improved now. So that is why what we said is only on Linux we are looking at how many large pages are allocated inside the guest. So we will adjust our ballooning accordingly. It is not required for Windows.
That's why your graphic shows a better utilization on page sharing memory in Windows than in Linux.
Yeah, in Windows, the another thing that happens is it zeroes most of its free pages, and it has a zeroing thread which goes and zeroes pages, free pages. So we can collapse all those 0 pages using page sharing. So whereas in Linux, oftentimes it does not do that.
Okay, thank you.
Here. In the TPS, in order to dedupe the pages, first of all, it calculates a hash. It compares the hash, and afterward, if the hash are equals, compare bit by bit. Okay?
Yeah.
In which moment does the hash calculation of the pages?
So we periodically, like that scanning thread that we have, we periodically take a random page and compute the hash. And then if there is no matching page, we put it into a hash table, right? And then later, some other random page we picked up, and then we computed the signature, the hash. And then now we go and compare into the hash table, check the hash table, and then see, oh, there is a matching page sitting there. That time we take the old matching page and this page and compare bit by bit. And then make sure that they are really identical, because we want to avoid hash collisions. Because of that reason, we do a full compare. Then we know that, okay, these 2 pages are identical. Then we share those pages and then mark them as read-only.
Okay, and another about ballooning. When there is a lot of free memory or idle memory inside the guest is candidate to be borrowed by the hypervisor to lend memory.
Right.
Okay. What happens if the hypervisor borrows some gigs, for example, and afterward that guest is under pressure and needs those pages?
Right.
How does the hypervisor know that the guest is now under pressure?
Right. So what will happen is, say that you have to give an example, you have a 20 GB guest, and there it was completely idle. We ballooned 10 GB out of it, right? And then what happens? Guest load picks up, and then now the remaining 10 GB guest can allocate, because the 110 GB we have ballooned out, but the remaining memory it can allocate and start using heavily. Then ESX is continuously doing this active estimation for the VMs. So it knows that, oh, okay, this VM has started some workload, and now it is touching this 10 GB very heavily. So let me try to give more memory to this VM. So we'll try to unballoon or deflate the balloon, and then and we slowly pick up the information that guest is actually now is doing a new workload, and we will reduce the balloon. We'll deflate the balloon.
Okay, and the last one. Is there any way to see how much memory is the entitled memory in one moment of the VM?
Yeah, I think entitlement number should be available on one of these VC ops or VC UI. So you should get the entitlement number.
It's in resolve.
Okay, thank you very much.